In this video, we introduce machine learning and the basic techniques which are used in machine learning. In machine learning, traditionally, two problems are addressed. One is classification, the other is regression. There is observation X, which may be a vector of dimension n. Let's say they are real valued. Examples could be images. Image can be two-dimensional, a matrix kind of thing, but it can be vectorized. Text will be vectorized by itself. In any case, either one of these can be converted into an X belonging to some R raised to n, where n is appropriately fixed. These are also called input features, and n can be the number of features. Corresponding to each X, we have to put a label. We have to assign label to X, and that needs to be done by the machine. If the machine is acting as a classifier, then Y will be a finite number of labels, 1, 2, up to n, and is some finite number. For example, it could be like images, and you are talking about the classification of objects seen in the images. It could be table, chair, cat, and so on. One very important classification of objects in images is face recognition system. So there is in that, and in each image, there is face of a person, and the machine has to classify which person it is among a given number of people. For text recognition, there can be letters which we have to recognize or words. It could be in handwritten text and so on and so forth. The learning is the machine needs to be taught how to, for example, classify objects given in an image by assigning it a label Y. For that, first machine has to be trained for that kind of data, for that kind of application. For training images, we use training set x1, y1, x2, y2, up to xm, yn. So there are m elements in it. Xi's are the observation and y's are the labels assigned to it. These are training set where for each image, for example, xi, what are the objects in that are given in the yi. And machine is provided the sample to learn from for that particular application. This kind of approach in machine learning is called supervised learning, where xi, yi are given in the training sample. If the labels yi are not given and only xi are given, then it is called unsupervised learning. In this video, we'll be talking about supervised learning, which is the main method or main approach of machine learning. First, we'll talk about the classification. At the end, we will discuss the regression problem. In classification, and we will be talking about supervised learning, there are, in general, 4 methods. One is the k nearest neighbor, called KNN. Next is support vector machine, SVM, and they are generalization by kernel methods. Then there is random forest, and finally there is neural networks. Historically, the first 3 methods have been the most popular, but since 2010, neural networks have started becoming the method of choice because they have been shown to outperform in many different applications. So in this video, we'll be talking about the first 3 methods. The neural networks will be discussed in next 6 videos in much more detail because those are the method of choice right now. In k nearest neighbor, k is a positive integer. One can take it to k is equal to 1, 2, or to some m. And the observations x belonging to Rn are given some norms. L1 norm is the summation of mod of the components of x. So x has component x1 to xn, and you take their modulus values, take the summation, that is L1, and L2 take the xi squares, sum them up, and then take the square root. Distance between x and x prime, 2 points in Rn given by the norm of the difference x minus x prime, and the norm could be L1 norm, L norm, where L1 is this and the L2 is this. Of course, L could be taken any positive number greater than equal to 1 as well, but these are the norms we'll be discussing, and more often, in fact, is the L2 norm that we'll be talking about. So in K and N, to classify a new observation given the training sample x1, y1 to xm, ym, we take the distance of x from each one of the xi's and then find the training sample xi which are closest to x. So we find k of them, k closest. If k is equal to 1, find the closest. If k is equal to, find the 2 closest, and so on by this distance. And now look at the labels of those k nearest neighbors. Among those labels, find the majority label. So suppose there are 5 labels and 3 of them are class 2, then x, which we want to classify, will be classified as class 2 observation. This method is very simple. There is really no training required. All you need is a training sample. However, it is surprisingly effective, and it is one of the oldest methods in machine learning. There are efficient algorithms available for finding K and N, and there is a well-developed theory for this. It can be shown as the number of observations, samples, M in the training sequence increases, the K chosen should also be increased for good performance, and it should be increased in such a way that if m tends to infinity, k should also tend to infinity, but slower than m, so that k by m tends to 0. Example of this, let's take two-class problem. So yi labels will be 1 or 2. Data is in R2, and k we choose is 3. So 3 and n. Suppose you want to classify x 1, 1, and 3 nearest neighbor in the training sequence are 2, 1, 0, 0, 0, 2, with the corresponding labels 2, 1, 2. So among the 3 labels, the majority label is 2, therefore x will be classified as 2. Similarly, if x is equal to minus 1, 1, which we want to classify, and it has 3 nearest labels, minus 2, 1, 0, 0, minus 1, 1, with all having label 1, then of course x should also be classified as 1. Next method is decision tree and its generalization random forest. Decision tree we will explain by an example. In this, from the training data, so you start with the training data, we form a decision tree. And then classification of any point x, observation x, will be done by the decision tree. And how this decision tree is formed as follows. We consider the example where x in an R2 with components x1 and x2, and there are 5 classes. Y labels are 1, 2, 3, 4, 5. In the classification is done as in this picture. In this picture, x1 is plotted this way, x2 is plotted this way, and A1, A2 are labels on this, A3 and A4 are given here. If the data point x falls in this rectangle, then it will call class 1. If it is in this rectangle, then it will class 2, and so on. Now, if you corresponding to this example for classification, a decision tree can be made as follows. So decision tree will start, if you want to classify any observation x, at the root node. We'll start here, here. If the point x with component x1 and x2, if component x1 is less than a2, where A1, A2, and A3, A4 are given here. If X1 is less than A2, if the answer is yes, then you again consider X2 component. If that is also less than A2, if the answer is yes, then X will be classified by S1 or class 1. As you can see from here, if X1 is less than A2 and X2 is less than A4, then that X falls in this and the class is X1. If X1 is less than A2, yes, but X2 is not less than A4, then the class will be S2, as you can see here, and so on. This is called the decision tree. The data will have to be fed from here, and then the questions are asked, and the nodes, depending upon the answer of that, you keep going further to the children nodes. And as you reach the leaf node, each leaf is given a class. So once the X given that you want to classify goes to a leaf, then that's the class it is given to. Advantages of decision tree, these are fast to learn. Given the training sample, the fast algorithms are available. They can, an important thing is handle numeric data as well as categorical data. So numeric data is if the observations X belong to some Rn. So these are real valued vectors of length n. But often in applications, the data X is not having real values, but some categories. For example, if you want to classify fruits in an image, then the X could be the color of the object in it. So the color may be yellow, green, and so on. The second component of it may be the shape of the object. It could be circular, rectangular, and triangular, and so on. So if X is categorical and not numeric, then KNN cannot be used. However, the decision tree can be used because, and the questions that are asked at each node, like xi less than ai, could be thought of questions like is xi yellow, or color of the xi yellow or green, and you can go that way. So decision tree can take care of this. They scale well with the large data sets when training sample is m is large, or the dimension of x is large. It's easy to explain. It's an important point because once a point x goes through a decision tree till it reaches the leaf, that whole sequence of questions that are answered explain how the decision was made, and this can be understood by the human beings. As against that, if you use KNN and the other method that we are going to talk about, decision may be there, the performance of the disease classifier may be good, but it may be difficult to explain to human beings. And in certain applications, it's important to explain. For example, in medical applications and legal applications, a doctor has to explain to a patient how the decision about certain disease was made, even if it was done by a machine. Last point here is that the decision tree we have considered here are binary decision trees. These are decision trees that each node has two children, or it is the leaf node. Leaf node does not have any child. One could have considered decision trees where a node may have more than two children, but it is decided based on practical experience that it is better to use decision trees because these are easier to learn and computational requirements for classification are less. The performance of the decision tree may not be as good as the other methods that we have talked about. However, its performance can be improved by using random forest, which we are going to explain in the next slide. Now, the last point is, and this is the important point, So we told that how using a decision tree observation X can be classified. Now the question is how to make that decision tree, how to learn that decision tree. And remember, depending upon what kind of decision tree is, its performance may or may not be good. So we want to design a decision tree or learn a decision tree which will provide good performance. And it needs to be done from the sample S given to us, which is x1, y1 to xm, ym, xi with the observation with the labels yi. And the decision tree that we want to make should be such that the classification error provided by this is minimized. However, given the sample as obtaining the optimal decision tree is a NP hard problem, which means that for large sample size and large dimensions, it will be practically impossible to get the optimal decision tree. In that case, uh, luckily, there is an algorithm available, which is a heuristic algorithm. It's called heuristic greedy. It's a greedy in nature, which is computationally not that expensive and has been found to work well, even though it may not provide the optimal decision tree. Therefore, in practice, this greedy algorithm is used to design the decision tree from the training sample. We are not providing in this video this algorithm, but this is available, well-known algorithm and can be obtained from any book in machine learning. Now, so as I said, the decision tree may not perform so well, but its generalization is provided by random forest. In random forest, instead of using one decision tree, we use multiple decision trees, and hence, a bunch of trees should be called a forest. So this is called a random forest. So instead of making one decision tree via the training sample, we make, say, T decision trees. T could be 10, 20, 30, and so on. And once we have that many decision trees for any observation X, we classify by all the T decision trees. So let's say X by decision tree Ti will give class Ci. Then the final decision of X from the random forest is given by taking the majority vote over the T decisions given by the T decision trees. Now, how these decision trees T1 to T are formed? Each one of these decision trees will be formed via the greedy heuristic algorithm that we have mentioned earlier. However, what we do now is to make any one of the decision tree, let's say Ti, instead of using the whole training sample, as let's say S has 1,000 samples, we take a subset, let's say S prime, and maybe it has 100 samples. You pick 100 samples, training samples out of the 1,000 randomly. And then out of the n features that each of the xi's has, we choose only square root of n features. So if n has 100 features, we choose 10 features out of them to make the decision tree. Remember, in decision tree, at each node, we are asking a question like xi less than ai. So those features xi, we could have picked out of n any of the n features, but rather than picking from any of the n, we'll now pick from square root of n features that we have randomly selected. Now for each ti, this is what we are going to do. A random subset S prime is selected and a random number of features square root of n are selected and the decision tree is made. So this is how you make, let's say, T1. To make T2, again, independently, randomly, we pick a subset S prime. Independently, randomly, we pick square root of n features and make T2. Making this way, the different trees that we'll obtain will be approximately independent. And choosing these independent T decision trees to make final decision provides a better algorithm than choosing just one decision tree based on all S and N. Next, we talk about support vector machines, SVM. SVM are originally provided for binary classification where labels yi will have value -1 or 1. Xi, the observations are vectors of length n. And we have a training data x1, y1 to xn, ym. SVMs are linear classifiers. So what we mean is take the x, you make linear function, linear product of w with x plus b, where w and b are fixed. Depending on the w and b, a different linear function will be obtained. Now, after this getting linear value x corresponding to x, we take a sign of that. If this value is positive, sign of this will be +1. If this value is negative, the sign of this will be -1. Thus, sign of this quantity will give us a classifier for x, which is +1 or -1. Of course, choosing how good this classifier will be depends on how we choose W and B. So what we do is, from the training data, we try to get the optimal W and B, which will give the best classifier. How it is done is by solving this optimization problem. If this training data is linearly separable, that means there is a W and there is a B, such by choosing that and using this classifier, we will be able to classify all the training data properly, which means that they will give the same value as the yi. If such a WB exists, then this is called linearly separable. Now, if the data is not linearly separable, then obviously such a WB does not exist. If it does exist, this optimization problem will give the the best WB. That is, you minimize half norm L2, will take L2 of square of W, subject to inner product Wxi plus B multiplied by yi greater than or equal to 1 for all I, the samples xi, yi. How this constraint comes is, if yi is positive and this quantity is positive, then sign of then will also be positive, and therefore it will be a correct classification, and the product is going to be positive. If yi is negative and sign of this quantity is also negative, then the product of this is again positive, and so the product here will always be for all I greater than or equal to 0 if that WP is if that W and B are providing correct classification. So we solve this optimization problem. Of course, as I said, for correct classification, this needs to be greater than or equal to 0 only, and not necessarily greater than or equal to 1. But this can be ensured for any proper classifier if we do the pre-processing of the data. And that is, for any W and B we choose, find x naught in the training data that is closest to the hyperplane of WB. The hyperplane is obtained by W x naught plus B. So you calculate this for all xi, find wx, which is closest, which has the smallest value. And then you normalize WB such that this quantity is equal to 1. If you do this pre-processing, then it becomes this requirement in the constraints for correct classification. This optimization problem is a convex quadratic optimization problem with linear constraints. So this is one of the simplest optimization problems, and efficient algorithms are available to get the optimal point. The optimal point we will denote by W star and B star, and they can be obtained by solving what is called KKT condition, Karush-Kuhn-Tucker conditions, which generally, of course, cannot be solved in closed form needs to be solved numerically. And once you do that, you obtain the optimal solution. If the data is not linearly separable, in other words, there is no W and B which will classify the whole data correctly, then we modify the above optimization algorithm into minimizing this function. Here, minimum, earlier minimum was over this only. Now you add to this another plus C summation of zeta I, whereas zeta I are non-negative, and the constraint that we satisfy is this is the previous function. And earlier the constraint was greater than equal to 1. Now we relax it to greater than equal to 1 minus zeta I, where zeta I is greater than equal to 0. We solve this optimization problem. Then it will provide a solution WB, optimal solution. Uh, Otherwise, the previous optimization algorithm, if the data was not nonlinear, will not provide any solution, because there will be no feasible WB satisfying the constraints. So this modified optimization algorithm is problem is still convex optimization problem and can be solved by the KKT conditions using same algorithm that we have mentioned earlier. However, for the general linearly non-separable case, the optimal solution provided by the above method may not provide a very good solution. So in that case, we can use kernel methods which can provide better algorithms. Now, the whole idea of the kernel method is the following. The original xi's are in Rn, and we don't have any linear classifier which does a good job in classifying them. So what you can do is you take a mapping, nonlinear mapping. It needs to be nonlinear mapping from Rn to Rn1, where Rn1 is much larger than n. So you take a nonlinear mapping to a larger dimensional space. Now the chances are that once you have projected xi on this larger dimension space, and we consider training data in this larger space, then the data may be much more linearly separable than in the original space. And after you have in projected in the larger dimensional space, we can use SVM on this, and the optimal solution that you will obtain hopefully will have a much better performance. Now, of course, the optimal solution are going to obtain via the optimization algorithm, this more general algorithm that we have given here. Example of this, and this claim that in larger space we may be able to linearly separable. So this is one example. Let's take x2, x in R2, and there are two classes, and there are two samples, four samples. Sample 1, 1 and minus 1, 1, minus 1 have class 1, minus 1, 1 and 1 minus 1 have class 2. Now, if you plot them here, this is first component, this is the second component, x2. These represent this class. These represent the second class. Looking at this data, you can see that there is no linear line which will classify these properly. You can, in fact, mathematically prove it. Now, what we do is we take a mapping, nonlinear mapping phi from R2 into a larger dimensional space, that is to R6. And this is given as follows. If x is x1, x2, then phi x is given by x1, x1, x1 square, x2 square, square root of 2, x1, x2, square root of 2, x1, square root of 2, x2, and 1. So these are the 6 components. Out of these 6 components, if we take only the third component and the fourth component and plot them, this is third component and this is the fourth component, you see that class 2 are these 2 points and class 1 are these 2 points. Now, unlike in this case, in this transform domain, This is, you can linearly classify them by taking the vertical line, this vertical line. Okay. So, of course, the issue is how to get this phi. This is a critical thing. Here, it may not be that difficult to get it, even though, this was not easy to get from first principles. But it will become much more complex if the number of data that you have is large and the dimension of X is also large. So getting this nonlinear phi can be extremely difficult, and this was one of the reasons why we use the linear classifiers in the first place. Secondly, even if we get phi, properly classifying in this larger dimension N1 space will have much higher computational complexity. If we use the kernel method, then both of these issues can be addressed. Kernel is, so X are in Rn, so kernel is a mapping from Rn cross Rn to R, any mapping. If it is called, it's called positive semi-definite symmetric kernel if for any integer L positive and for any Z1 to ZL points in Rn, we make this L by L matrix where the ijth element of K is K, Zi, Zj, where Zi, Zj are taken from here. If this matrix, L by L matrix that you get, if it is positive symmetric definite for all such L and also Z1 and ZL, then K is called the positive semi-definite symmetric kernel. Well, you may ask, this seems like a very strong assumption, but there are very nice examples which satisfy this. Suppose you take k x prime is the inner product of x and x prime plus c raised to power a, where c is a real number and a is a positive integer. We can say that it is satisfying all the conditions required. Then this is Gaussian kernel, where kxx prime is exponential minus norm of x minus x prime square. The norm again here will be taken as L2 norm divided by 2 sigma square, where sigma greater than 0 is fixed. So this is the Gaussian function. That's why this is called Gaussian kernel. And these are two examples of commonly used kernels. So once we have chosen for our problem a symmetric, semi-definite, or semi-positive definite kernel, it could be one of the above kernels, then this theorem, this is a theorem, says that there exists a mapping phi. It's a nonlinear mapping from Rn to Rn1, where n1 is larger than n. Often n1 is very large, such that k x prime is inner product of phi x prime. In other words, this k is inner product in the transformed larger dimensional space. Now we start with some suitable k. Correspondingly, we have this phi and this space here. And in this space, this larger dimensional space, we take the training sequence. Now this training sequence is phi x1, y1, phi xm, ym. So label stays same, but xi becomes phi xi. In this space, we use SVM to get linear classifier. And the hope is that in the larger dimensional space, the data is much more linearly classified, and getting the optimal linear classifier in this modified space can give much better performance. However, as we said earlier, solving SVM in Rn1 can be far more computationally complex. So that's where the kernel trick comes now. By using these kernels, we fixed kernel K appropriately, phi and R1, N1, we don't even have to look at. And we can solve the optimization problem of SVM in the transform domain using these kernels. And the solution is given by, the optimal solution is given by sine of sigma alpha j star yi norm inner product of xj x, where xj and yj are the training data, plus p star. Alpha j star and b star are the optimal points obtained via KKT conditions, in fact, solving the dual condition. Now, using this, in fact, this optimization problem of SVM in Rn1 has been reduced to the optimization problem in Rn itself. However, the solution obtained now will have the effect of getting SVM in the larger dimensional space, and hence the performance will be much better. Here, of course, this inner product is given by the kernel chosen there. So the kernel methods can provide computationally competitive algorithm and performance as competitive as with the random forest and so on. This SVM and kernel method has been described for binary classification, but it can be generalized to multi-class classification via techniques called one versus all and one versus one, which again are available in the literature. And therefore, this does solve the multi-class, general multi-class optimization classification problem. Final comments on the classification part. Random forest and kernel methods have been very successful and popular. And in fact, they were the methods which were being generally used in machine learning till 2010. Since then, deep neural networks had slowly taken over when there is much more data and much more computational power. If training data is not enough or computational power is not much, then we may still want to use random forest or kernel methods. But if both of them are in abundance, then deep neural networks will perform better. And this has become, in fact, the method of choice now. And therefore, we will spend much more time on deep neural networks in next 6 videos. Now we'll look at the regression problem. So remember, classification regression problem are two classical problems that have been looked at in machine learning earlier. And so far in this video, we have talked about the classification problem. Now we discuss the regression problem. Regression problem is the following. Remember, xi and yi are the samples, xi are the observations, and yi are the corresponding labels. If it was a classification problem, yi will belong to 1 to n numbers, but in regression problem, x belongs to Rn, and y may also be a real value, where x and y are related by y is equal to m naught x plus z, where z is some noise independent of x with mean 0, and m naught is some function, can be a nonlinear function. M naught is the unknown quantity here, unknown function here. We start with xi, yi training sequence, and we want to estimate m naught from the training data available. And we train the machine so that the machine will provide this estimate of m naught at any given point x. So we can consider this training data x1, y1 to xn, yn as independent, identically distributed random variables with some unknown distribution. These are statistical assumptions which in machine learning or AI are usually not made. However, these assumptions come from statistical machine learning, but the algorithms that we use don't actually make use of these assumptions. These are used only in the computing the theoretical performance of these methods. Just like for classification, for regression also, we use the same methods, KNN, random forest, kernel method, and neural networks. As before, In classification, random forest and kernel were the most used method till 2010, but now neural networks have taken over. So in this rest of the video, we are going to talk about the first three methods for regression, as we have done for classification, and neural network methods we will leave for later videos. So KNN for regression, we have the training data x1, y1 to xn, ym, and we want to find, estimate m naught x at some given x. So as before, out of the data corresponding to x, we find the k nearest neighbors in the training sequence, x1 to xm. Let's call these k nearest neighbors as x1 prime to xk prime. And then the estimate of m naught x given by m naught hat x is the average of the labels corresponding to this x1 prime to xk prime. You take add them up, divide by 1 by k. This is the average, and this is going to be the estimate by KNN. In random forest, we again start with generating T trees, T1 to TT. These will be generated, as in the case of classification, through the training sample using the greedy heuristic. Once we have these trees and you want to estimate m naught at point x, take this x, you push through each of these trees, pi, and you will go to all the way the leaf. And in that leaf, if x1i, y1i to xmi, ymii are the training sample available in that leaf, where x lands up in ti, then the estimate mi hat x of m naught x from tree ti is given by the average of the labels in these samples. So for each of the TI, you compute mi hat x, and for the random forest, you take the average. And that is m hat x, the estimate of m naught x from the random forest. In kernel method, choose kernel k as before. Then we'll have a feature map phi, and here h denotes the higher dimensional space, Rn1. And now, for a given w, in h, the estimate of m naught x is given by m naught hat x equal to wt, inner product of w with phi of x in the transform domain. So we find w which minimizes this. And what is this? You compute the estimate corresponding xi corresponding to a given w, find difference from yi, take a square, sum them up, and add to that this regularization condition, lambda norm of w square. You find w which minimizes this, and that w you use here to get the estimate m naught x corresponding to this kernel. So we have explained the three different very popular methods in machine learning for classification and regression. Now there are more advanced topics in ML, AI, which will be talked about in the advanced part of the module. These are reinforcement learning, which is very, very important. And this is used for more advanced applications of machine learning and AI. For example, getting a program like chess program to play good chess, or autonomous vehicle, driving an autonomous vehicle, you need something like reinforcement learning, causality that tells the effect and cause in overall setup of the world that we are forming for our application. Transfer learning, is very important. We will also learn that in the advanced part. Transformer architecture has become very popular recently in NLP, natural language processing, like things like Chat GPT, which are very, very popular and have made AI very popular recently, uses transformer architecture. We'll study that as well in the advanced topics. Generative AI is AI which generates new images, new data. This can be used to augment the training data to train the machine. For example, when there is not enough training data, if there is not enough training data, the optimal solution that you obtain from the training may not provide good enough performance. So you can synthetically generate through AI new data, which can is further be used to get better classifiers. This is done by what is called generative AI. Explainability is another very important topic which we have discussed earlier also. This explains the logic behind the classification done by our machine. And this has become very, very popular. We will explain that as well. And the final topic which we may talk about is graphical neural networks. This also takes care of certain kind of applications which are not taken care of by the usual applications. Thank you very much. I hope you have learned enough of machine learning in today's video. Machine learning, as we said, is an important part of the AI systems that one may want to design.